Welcome to the new lecture of Robotics and Controls. This is lecture 5 and today we are going to discuss inverse kinematics of manipulators. So before starting with inverse kinematics, we'll first try to understand a tool which is useful in solving inverse kinematics problems, which is root finding. This is a precursor to the inverse kinematics because in inverse kinematics the problem that we have is we have been given the coordinates of the end effector, that is q naught, with respect to the fixed coordinate frame, and we need to find the joint angles theta 1 and theta 2. And to solve this problem, root finding is an important tool. We need to find the roots of an equation. Let's try to understand this with an example. Fx equal to x square minus x minus 2, a polynomial function. The roots of this polynomial is the solution x of the equation fx equals to 0. If we try to make the graph of this function or this equation, you'll see that it will cut the x-axis at 2 points, -1 and 2. So for this particular equation, it was easy to find the solution or the roots, but this is not always the case. Sometimes it's hard to find the roots of a equation analytically. So we will use a Python function fsolve to compute the solutions of fx, and we'll later use this same function to solve the inverse kinematics problems. Now let's transfer to the Python environment. Now we'll explore an example of finding root of a function using the fsolve from the SciPy library. We will later use it to solve IK problems. To get started, we'll need to import the following libraries. SciPy for the fsolve function. If you do not have SciPy installed, you can download it using pip install SciPy. We'll also import matplotlib for plotting the functions and numpy for numerical operations. Now we'll define a simple function fx that we discussed a little while ago, x square minus x minus 2. Now we'll create a list of x values and the corresponding function outputs, which we'll later use to plot the functions for visualizing. So y is equal to function x. Now let's write the code for plotting the functions. So first let's define the figure 1, and now let's plot x and y. Now we'll give the labels to the axis. Plot x label x, plot y label y, and now we'll give the title. Now we'll write the code to so that the plot appears on the screen for some time, let's say 10 seconds, and then it closes automatically. Now let's plot the function once. Run the code. Python 3 example underscore roots.py, and here is the plot. So you can see it's difficult to find the root just by visualizing. Let's add grids to this plot so that we can see where the curve intersects the x-axis. So yeah, you can see there are grids, and at x-axis it intersects at 2 and somewhere between -2 and 0. Okay, now we'll use the fsolve function to find the roots. So let's solve the equation. So the way we use fsolve function is we fsolve, in the bracket we write the function and then we give the initial guess. So let's say we give the initial guess as 3 right now, and it returns the solution, and we'll print the root as well. Now let's run the code. We'll just comment show so that it closes automatically and then gives us the answer. It prints the root. Yeah, you can see it gave the root as 2, and now let's try to change the initial guess and see what change happens. Does it change the root or not? So yeah, you can see if I change the initial guess to -2, it changes the root to -1. So initial guess is really important. fsolve returns the nearest solution to the initial guess. Now let's move back to the pen and paper to define the inverse kinematic problem, which we will solve later using the fsolve function. Now let's discuss inverse kinematics of a two-link manipulator. So let's draw the two-link manipulator first. So this is the first link, this is the second link, and this is the end effector. Let the solid lines represent the current position of manipulator and dotted line represent the reference position where we want the manipulator to go. The theta joint angles in green represent the reference joint angles, and the joint angles in red represents current joint angles. And we want the manipulators and effector to go to xref and yref. For IK problem, we want to compute joint angles theta 1 and theta 2 such that the end effector Q is at xref and yref finally. Mathematically, if we want to define the problem, we are given xref, yref, L1 and L2, and we want to find the joint angles theta 1 and theta 2. Now, this is the IK problem. Now, let's try to write it in a way so that we can code it up. So the coordinates of the end effector Q in fixed frame is we calculated it in the forward kinematics class. It's given by this, and this should be equal to the reference coordinates of end effector xref and yref. L1, L2, xref and yref are given constants, and theta 1 and theta 2 are the variables. So it's a two equation, two variable setup. Now let's define a function f whose roots will represent the solution to this IK problem. So it will be given, will bring the reference coordinates on the left hand side, x coordinate minus xref and y coordinate minus yref. And now let's try to use this equation in Python environment. Here I have written a piece of code in which I want to calculate the inverse kinematics. I have not written the inverse kinematics code as of now, but I have taken the forward kinematics from the previous code from the previous lecture and converted it into a function. So let me explain the code now. So here are all the libraries that I have imported, and here is the forward kinematics function. It intakes the theta 1 and theta 2 and gives me the coordinates of O, P and Q points. He, Here you can see there is a reference L1, L2, XRF, YRF, and we want to calculate theta. So the way we want to calculate it is using inverse kinematics function, which intakes L1, L2, XRF and YRF and give me the theta back. But we haven't written this function as of now. We'll write this function. So let's define the function inverse kinematics. Um, but we discussed that we want to calculate it using the roots of a function. So let's right now pass this function and first write the function itself, whose roots will give us the inverse kinematic solution. So function to solve for theta 1 and theta 2. So let's define the function f. It intakes theta and gives us back the equation basically, or the function whose roots are the solutions. So we also intake the parameters as a list, basically L1, L2, XREF and YREF as a list of params or parameters. And now we use forward kinematics to calculate X and Y. So basically um, the current position of the manipulator. So this will give us the manipulator's position in general sense of theta 1 and theta 2, and um, we save them in x and y, and the equation is given by x minus xref and y minus yref. So this is the function. The roots of this function will give us the inverse kinematics solution. Now let's use this function. Let's solve this function in inverse kinematics. So the way we solve it is the theta equals fsolve, the function itself, the initial guess. So let the initial guess be 0.01 and 0.5. And we also have to give the values of parameters because the function fsolve doesn't know these are fixed. So we give parameters and define it in the above line L1, L2, xref and yref. Now we return the thetas. Basically theta index 0 and theta index 1, which are respectively theta 1 and theta 2 of our manipulators. So we save these values in two variables, theta 1 and theta 2, and we print them. So print theta 1 and print theta 2. Okay. Now we have written this code. Let's try to run this code and see what it gives us as an output. So Python 3 manipulator inverse.py. Yeah, so we got two values, theta 1 and theta 2 in radians. One is minus 1.31 and the second is 2.63 radians. Now let's try to change the initial guess and see if it changes our output. So right now it didn't change the output or the inverse kinematics solution. Let's change the theta 2 coordinates of the initial guess also, and you can see that it changed the solution. So for into our manipulator, there are always two solutions for a given reference point. Yeah. Now let's try to plot this manipulator. So plot the 2D manipulator. We'll use similar concept that we have been using. So we want to like plot the inverse kinematic calculation. So we'll first we use the theta 1 and theta 2 that we have calculated to plot the forward to get OP and Q using forward kinematics, and use the plot function thereon to plot everything. This line plots the link 1 of the manipulator. We copy paste it and plot the link 2 as well. So we just change the points. So you can see the first plot gives us a line from O to P, and the second plot gives us a line from P to Q. We change the color to blue, and now let's label the axes. So it's similar stuff that we have been doing in our last programming examples as well. Um, we'll set the limit of the plots so that the plot is limited to some x and y coordinates, and we'll also um, show the grids so that we can know if the end effector is at the right point just by visualizing it. We'll also set the aspect ratio so that the aspect ratio to be equal, so that the window seems like it's a square, and then we'll use pause and close functions so that the window opens up, stays there for some time, and closes automatically. So here you can see we plotted the function. The manipulator gives us the theta and it plots properly. Now let's change the initial condition and see. Yeah, so you can see there are two solutions. There are two solutions to reach the same point, and fsolve gives one of them. Yeah, let's change the initial guess back to where it was. And now let's try to give a different reference point. And yeah, so you can see it is giving us what we want. It's plotting properly. Now let us use this inverse kinematics code to trace any curve using the manipulators and effector. So we copy this manipulator inverse.py code into a new file, manipulator inverse underscore circle, because we want to trace a circle using the um, using the manipulators and effector, and we'll modify this code little bit to do that. So now let's instead of xref being a point, the reference point being a point, it's a curve. So let's define the curve in a parametric form. So we define a list of angles phi from 0 to 2 pi with difference of 0.1 radians on each, and xref is basically the equation of a center is the center's x point plus radius into cos phi. So here center is 1 comma 0.5 and the radius is 0.5. So this is the equation of a circle. Now we'll define an empty list in which we'll store all the inverse kinematic solutions for each point of this curve. So for each point on that curve, we'll have some theta 1 comma theta 2. Now let's solve the inverse kinematic problem inside a loop and solve the inverse kinetic problem for each reference point. So we do that by taking each point in a of the each reference point and solving the inverse kinematic problem and storing it in theta 1 all and theta 2 all, and remove, we do not need this print statement. Now let's use the for loop to plot the same concept that we use in our animation video. We'll use the flip book concept. So we'll now plot these function as it is, just changing a few variables here and there which is required. And now what we'll have to do is we'll have to name these link 1 and link 2 in order to remove them in each iteration so that it feels like it is an animation. So now we'll remove them. So link 1 underscore plot dot remove and link 2 underscore plot dot remove. Okay. We'll also pause only for 0.05 seconds so that it feels like it's an animation. We'll also plot the trajectory of the end effector. Here it is circle, so we'll just plot the point Q. And we'll not remove it so that we can see if it is tracing a circle or not. So we'll plot Q and give it some color black, give it some marker O, let's say, and we can give it some size 3. Okay, now this is the code written. Let's run this code. Python 3 manipulator underscore inverse circle. So there's an error. So I think there is a typo in a range. So yeah. Okay, now let's run the code. So you can see it is tracing the circle, but there is some flicker. So we'll remove the grid and now we'll run it again. So now you can see it is tracing a circle. All right. Now what we can do is we can change the center and also the radius. So we'll write here the x coordinate of the center and the y coordinate of the center, and we'll also fix the radius. So here we can write the radius. We'll change the center to 0.5 and 0.5 and radius to 0.3, let's say. You can see the news, it's also tracing the new circle. We can also convert it into an ellipse. So instead of single radius, we can convert it into 2, and you can see it traces an ellipse as well. You can reduce one of the radiuses and it traces the ellipse as well. So you can play around with these codes according to your own requirement. I have attached the link to these codes in the description section. You can have a look at them. And if you have come till here and learned something useful, please subscribe to the channel. See you in the next lecture.